Hi everyone, we're finishing up section 3.3 on log properties, and we're going to finish here with the change of base formula. All right, so how do we get from one type of logarithm to another? For example, how do we get from log base 2 to natural log, and vice versa? All right, so for example, we know that log base 2 of 8 is 3. And why is that? Because 2 to the what gives us 8. Well, 2 to the third gives us 8. Remember, logarithms are exponents. Now let's say we want to approximate log base 2 of 9. So instead of the 8 here, we're now asking 2 to what exponent will give us 9. Now, whatever number goes in that box, we expect it's going to be a little bit bigger than 3, right? If 2 to the third is 8, we expect 2 to something a little bit bigger than 3 to be 9, right? Because log base 2 of x is an increasing function. Okay, well, unfortunately, we don't have a log base 2 button on our calculators. By the way, in computer science, log base 2 is very popular. It's very common because they deal with base 2 a lot in computer science. Sometimes in computer science, they refer to this as the LG function, like a binary log function. Okay, well, it turns out there is a way to approximate log base 2 of 9. It's going to be an irrational number, so we're going to be rounding this thing off. So here is our formula. Okay, in fact, there are several ways you can do this. So we can say that log base 2 of 9 is ln of 9 over ln of 2, the natural log of 9 over the natural log of 2. By the way, that's not the same thing as the natural log of 9 halves. A lot of people get confused by that. These are not equivalent, okay? The log of a quotient is not the quotient of logs, it's the difference of logs. That's the quotient rule, okay? This is log base 2 of 9, which approximates to 3.1699. Try this on your calculators and make sure that you're entering this in and not this. This is not the same thing. Okay, so that's one way you can compute this. Another way you can compute this is by doing the common log of 9 over the common log of 2. Basically, the log of this over the log of that, whether it's a natural log or a common log. In fact, we can use a log with any nice base. It could be base 5 or base pi, as long as it's a nice base. So whether you use natural logs or common logs, you're going to get the same result here, about 3.1699. Of course, you must be consistent. Don't mix up log types. Don't put natural log up here and common log down there. You must use the same type of log in the top and the bottom. All right, so in general, we can say that log base 2 of 9 is equal to log base a of 9 over log base a of 2 for any nice base a. By nice, we mean positive and not 1. So in order to approximate this, we can use the fact that it's equal to the log of this over the log of that, where we use any nice base as long as we're consistent on the top and the bottom. Don't mix log types in this fraction. You could use log base 5, log base pi, you'll get the same result. Okay, if we want to make it even more general, or if we want to think in terms of a function of x, log base b of x is log base a of x over log base a of b. It's log of this over log of that, where we have the same nice base a. That's the change of base formula. And I don't care if that's x or a constant. This change of base formula will work. And remember, we only take logs of positive values. All right. Now, of course, our calculators usually have natural logs and common logs, so we're going to tend to use log base e, or natural log, or log base 10, or common log, since we can easily compute those on our calculators. But in principle, we could use log base 5 or whatever. In fact, if you have something like this, if you have log of uh, 20, let's see, 20, let's see, log base 25 of 125. It turns out that if you use log base 5, it's easier to work this thing out. All right. Now, another reason why we like the change of base formula is that it helps us in calculus. Remember that in calculus, we're going to use the fact that the derivative of ln of x is 1 over x, which is very nice. So in order to find the derivatives of other log types, we're going to use the change of base property together with this fact. Now, let's say you're a computer science major, some of you are, in algorithm analysis. Computer scientists may use this fact that log base 2 of x, or LG of x, that's a popular function in computer science, is ln of x over ln of 2. Or if you solve for ln of x and multiply ln of 2 on both sides, you get this. ln of x equals ln of 2, which is a constant, times log base 2 of x. So here we're saying that the natural log of x is a constant multiple of log base 2 of x. Likewise, here we can say that log base 2 of x is a constant multiple of ln of x. The multiplier here is 1 over ln of 2. 1 over ln of 2. That's the multiplier. So basically, you can say that any basic log function is a constant multiple of the natural log function. Now, computer scientists can get kind of lazy about this. Sometimes in algorithm analysis, they'll just say a log is a log. They'll treat ln of x basically like log base 2 of x or log base 5 of x or whatever. Basically, when it comes to matters of growth in time requirements or memory requirements, they'll just say a log is a log and they're happy. And they're happy that it's not exponential growth, for example, which can be very bad. And by the way, we have a proof of the change of base formula down here. It comes down to using the zigzag. So you have a statement like this, you zigzag it, you get that, and the proof goes from there. Okay, now I want to go back to this concept, the idea that any log function, basic log function, is a constant multiple of any other basic log function, in particular, the natural log function. Let's go to Desmos.